This video is about optimization. Optimization is where you try to achieve the best outcome possible given certain conditions. In this video, we are trying to maximize volume. Example 1, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? When you solve an optimization problem, you will usually write a primary equation and a secondary equation. The primary equation will represent whatever it is that you're trying to maximize, in this case volume. The secondary equation will reflect some additional piece of information that you're given. So the primary equation, since we're trying to maximize volume, let's write a volume equation. The volume of a box is length times width times height. So in this case, that will be x times h, which will be x squared times h. So there's your primary equation. For the secondary equation, we need to look for the additional piece of information that we're given. And here we see that the surface area has to be 108 square inches. Remember that this box has no lid. So an expression for the surface area will include the area of the bottom, which will be x squared, plus the 4 sides. So each of the panels on the side will have dimensions x times h. So there are 4 of those, so I'm going to say 4xh. This is an expression for the surface area, and we're told this will equal 108 square inches. So there's your secondary equation. Notice that the primary equation right now has 2 variables in it. Our strategy will be to rewrite the secondary equation, getting one variable by itself, and then we'll do a substitution, which will allow us to rewrite the primary equation in terms of a single variable. So let's see if we can get h by itself, and that's the substitution that we'll do. If we subtract x squared from both sides, we will have 4xh is equal to 108 minus x squared. If we divide both sides by 4x, we get h is equal to 108 minus x squared over 4x. Now let's make the substitution into the primary equation, and this will become v equals x squared times 108 minus x squared over 4x. Notice that the x in the denominator will cancel out one of these x's, so that will leave us with x times 108 minus x squared over 4. Dividing each of these terms by 4, we get volume is equal to x times 27 minus x squared over 4. And distributing the x, we get volume is equal to 27x minus x cubed over 4. Remember that our goal is to find the maximum volume, but we already know how to find the extrema. We use the first derivative test to locate the relative max. So let's go ahead and take the first derivative. So I'll just call it v prime, and that's going to give us 27 minus, I'm using the power rule, so the 3 will come to the front and become 3x squared. All right, the denominator of 4 won't change. So this is the first derivative. What we need to do is find the critical numbers by setting the derivative equal to 0. Normally, we would also ask ourselves where the derivative is undefined, but there is no place where this expression will be undefined. So we will set 27 minus 3x squared over 4 equal to 0. Adding 3x squared over 4 to both sides, we'll get 27 is equal to 3x squared over 4. Multiplying both sides by 4, we get 108 is equal to 3x squared. And then if we divide both sides by 3, we get 36 is equal to x squared. Taking the square root of both sides, we get x is equal to plus or minus 6. So let's just go ahead and break that down. We have x is equal to 6 or x is equal to negative 6. But remember, this x represents the width of a box. So this really cannot be a negative number in reality. That's going to be outside of the domain of this problem. So now I'm all set up to do the first derivative test. Notice I'm putting 0 on the left to represent the fact that x values cannot go negative. So this is like a brick wall, the end of the domain. So we have our one critical number. So we're going to need a test value in the first interval. I'm going to pick the number 1, which is just easy to use. And when I get to the next interval, I'm going to pick the number 10. Just a nice round number that's easy to calculate. So here's the first derivative. If I evaluate at 1, I'm going to have 27 minus 3 times 1 squared over 4. So that's just going to be 27 minus 3/4, because 1 squared is just 1. So obviously this is going to be a positive value. That tells us that the actual function will be increasing throughout this interval. Now, looking at the second interval, we will have 27 minus 3 times 10 squared divided by 4. So that's going to be 27 minus, 10 squared is 100. So this is going to be 3/4 of 100. And so that's going to be 75, right? 3/4 of 100 is 75. So we're going to have 27 minus 75, which obviously is a negative value. This tells us that the function will be decreasing throughout this interval. So that tells us that we have a relative max at 6. Not only that, it is the absolute maximum value on this interval, which goes from 0 to positive infinity. Remember that our goal is to find the dimensions of the box that will maximize the volume. So far we have found the x value that will maximize the volume. That's going to be 6. So we just need to find the value of h. We've already rewritten the secondary equation to give h as a function of x. So let's just let x equal 6 and see what h is. So h is equal to 108 minus 6 squared over 4 times 6. But that gives us 108 minus 36 divided by 24. So that's 72 divided by 24. So h is equal to 3. So with x equal to 6 and h equal to 3, the dimensions of the box that will maximize the volume are 6 inches by 6 inches by 3 inches.